All right, 9.1. This is our first section of chapter 9. It's pretty short. Let's just take a look at the notes together. All right, so 9.1, we're looking at introductions to matrix method for linear systems. All right, so first we look at this normal form. If the system expressed in this form, right, so we can see that on the left hand side we have x1, x2, and then up to xn prime. And on the right hand side, we just have the linear combination of the x1, x2 up to xn with some function based on t, right? A11t, A12t up to A1nt. So we have this system of equations. Then we can write that in the matrix form, capital A, and then each of the entry is just going to be the A11, right? Now these are going to be functions of t, and then you just put them in matrix form. And thus the solution is just going to be your vector x. Right now in in 9.1, we're just going to look at how we can come up with this matrix, and then later on we'll see or learn more about what we're going to do with this matrix right here. Okay, so let's move on to our first example. Express the given system of differential equation in matrix notation. All right, so this is what we have. This is the system we have, and basically your matrix A is pretty much like the augmented matrix for a system of equations, right? You just want to include, so each row is going to represent one equation, right? So if, for example, the first row is going to be x1 prime, second is x2 prime, and so on. And then you just need to put in their coefficients, the so-called coefficients, a function of t, right? So for the first row, we have 1, -1, 1, -1, right? These are the coefficients of x1, x2, x3, and x4. And then moving on to the second one, right? We have 1, 0, 0, 1, right? Because x2 and x3 are 0 in here. And then the third one, rat pi for x1, 0, and then -1 for x3, 0 for x4. And then last one, x for prime is 0, so 0 all the way. Okay, and we're done, right? That is the first example. Okay? All right, so let's take a look at example 2. Express the Drandre's equation as a matrix system in normal form. All right, so here we have a second order differential equation, right? Now homogeneous, right? That's not important. For now, we want to rewrite this as a matrix system in normal form. And let's do a quick review on normal form, which is this. A system of differential equation is in normal form if the system is expressed as this part, this collection of equation, right? So what we're going to do first is we're going to rewrite example 2, this equation, as a collection of different equations. And let's do that. All right, so here we have our equation. Now, notice that we only have y as our equation, and then, of course, the independent variable t. So in this case, we have to do a little variable substitution, right? So here, we're going to introduce a few more, introduce one more variable. And it's not as like introducing, just throwing a new variable, but we're going to rename just one of them. So here I'm going to let y prime be equal to some variable b, right? So now I have two different variables to represent our function using v and y, right? So we have a collection of v and y, right? So basically v is just y prime, right? But using v, then we can write out v prime is equal to something else, and then y prime is also equal to something else. And then these two equations will be our normal form. And then we can just use these two equations to come up with our matrix form. Now, the easy one is y prime, right? Y prime is just v, right? All right, now let's look at v prime. So to look at v prime, let's rewrite the original equation using v and y. Right, so we have 1 minus t square y double prime, that is v prime, right? Minus 2tv plus 2y is equal to 0. Now notice that the only variable with prime is the v prime here, right? The other two terms are based of v and y, so we can actually solve for v prime, right? To solve for v prime, and do move everything else to the right hand side. 2tv plus 2y is equal to 0, and then v prime is equal to 2t. Oops. 2t over 1 minus t square v plus 2 over 1 minus t square y is equal to 0. Okay. Now let me pause here for a second, and we will see two equations. Let's call that equation 1 and equation 2. And those two equations will give us our normal form. All right, next, let's put them in our matrix form. Right. So first, on the left-hand side of the system, we have y and v prime. All right, we have different ways to represent y prime and v prime. And it consists of a matrix multiplied by y and v. All right, so our first column is going to be the variable y, and then the second column is going to be the variable v. So in here, we just need to fill in the coefficient, right? So for example, look at y prime. Y prime is equal to v, right? So we have a 1 here, and then 0 for y. For v prime, we look at this equation. The coefficient of v is 2t over 1 minus t squared, right? So we put that here on in the second column, 2t over 1 minus t squared. And for y, coefficient of y, we have 2 over 1 minus t squared. So 2 over 1 minus t squared, right? And that is your matrix A, right? This is your matrix A. Right. So similarly for example 3, now example 3 is going to take us a few more variables, because we see y, y prime, y double prime, x, x prime, and x double prime. Well, we actually don't see x, right? But it's it can be done with a similar approach to as example 2. So let's take a look at that. All right, so to get started with example 3, right? First, we can look at, okay, so the highest order we have is x double prime and y double prime, meaning we might need to introduce some variable to replace those. And then we also have y, so y is going to be one of them, something to replace y prime, and maybe something to replace x prime. All right, so let's start from there. Let's say I want to use m to replace x prime, right? That means m prime is going to be x double prime, right? And maybe n to replace y prime, and then n prime is going to be y double prime. Okay, so now that's lists out all the variables we have. So we, at the end, we want x, y, m, and n, okay? Like that. Okay, and all these are the primes. Okay, and then that means we're gonna have something like a 4x4 matrix, right? And then each one of them is going to be based on x, y, m, and n. Okay, and then we're going to figure out what goes in here. All right, and let's do that starting with x prime. Okay, x prime is just equal to m. All right, so that means the only place that we're gonna have a value is the column that represents m. So let's do a quick note on the top: x, y, m, n. Right, to come up with these four variables, think about how you multiply the column into the matrix. Okay, so for x prime, we have 1 at m right here, and then everything else is 0. All right, and for y prime is defined as n, right? So we have 0, 0, 0, 1, right? 1 on the end. Now n prime and n prime is where we need to do a little bit of extra work to figure out. So let's take the first equation, right? Let's rewrite that using m and n. Okay, so x double prime, that is m prime, plus 3x prime is m, minus y prime, that is n, plus 2y is equal to 0. Okay, so let's move everything to the right hand side. We have m prime is negative 3m plus n minus 2y. All right, so m prime can be written as these three terms. So let's just take the coefficient and put it in here. All right, so m prime is equal to negative 3m. So m is negative 3 plus n. N is 1. Negative 2 on y, so negative 2, and then x is 0, right? Because we don't see x in there. All right, next, let's look at the second equation. All right, now this second equation is going to give us y double prime, which is n prime, right? Our last row here. So 2, right? And again, replace the second equation using our new variables. So y double prime is n prime plus x prime, that is m, plus 3y prime. Y prime is n plus y is equal to 0. Okay, and again, do the same thing, move everything and solve for n prime, negative m minus 3n minus y. Let me double check that again. Yep, looks good. All right, and again, just fill in the coefficient here. So n prime, first negative m. So on m, we have negative 1 minus 3n and minus y. And then again, oh, not minus 1, minus 1. My bad. And then the 0 here, right? So notice that on the first column, x's, we all have zeros because x does not appear here once, right? We see x prime, we see x double prime, but we never see x. That's why we don't have, we only have zeros here. But anyway, this is how we can convert just a regular differential equation into normal form and a matrix form. Okay, and that is 9.1. Very short, very easy. And then next week we will start with something a little more fun, what we can do with this matrix and how does it help us solve the differential equation.